All right, we're back with part two, and we left off last time talking about the tonotopic organization of the cochlea, which basically means what it says here is that individual hair cells in the cochlea respond best to particular frequencies within a general range of 20 hertz on the low end and 20,000 hertz on the high end. And again, just as a review, that cells at what is called the base of the cochlea respond best to high frequencies. So this is the 20,000 hertz end. And then the 20 hertz end is at the apex, so-called, of the cochlea, here in the middle of the coil. So how does this work? And it turns out there are different theories for what's going on here, each with their different proposals, and none of them kind of accurately captures everything we know about the frequency response of the cochlea. So we'll talk about more than one here to try to get a sense of what they propose and what they're good at explaining. So we can go back to the days of the 1800s and Hermann von Helmholtz again, Mr. Resonator himself, who first proposed that what's called the place theory of cochlear organization. So basically his idea was the simplest thing you can imagine, which is that there is one hair cell for each frequency, and that is, if you hear a frequency of like 1,762 hertz, it may pick out that one particular hair cell, and that's what sends that signal to your brain. This is also known as the resonance theory, I guess, because the idea is that that hair cell is resonating best at that particular frequency or something like that. But the problem with this one is that we can perceive more frequencies than we have hair cells for in general. So that line of, actually, I should go back and walk you through that. Remember, the inner hair cells, we have about 3,500 of those, but there are about 20,000 different frequencies that we can hear. So there's not enough individual hair cells to account for each frequency, basically. We have to have something more going on than just that. I'm going to add here as well that I mentioned these hair cells wind up being a little more sensitive to motions of the basilar membrane than these hair cells. And the point of that is that these hair cells kind of register whether or not there has been a sound at some frequency that pushes the membrane up at this point. And these guys are more for response to loudness. So if the sound is louder at that particular frequency, then these guys will start to get pushed up into the tectorial membrane and generate a response to the auditory nerve. So the more that these guys get involved, the louder a sound is going to sound. But these inner hair cells will basically let you know if there has been a sound that you can detect. But like I said, there's not enough of these inner hair cells to make the place theory work. So thanks, Mr. Helmholtz, for your resonators. But let's move on and maybe talk about different theories of how the cochlea works. So the rate theory emerged after Mr. von Helmholtz as an alternative. And the idea here was that rather than specific places being devoted to specific frequencies, the frequency of cell firing, the frequency of how often the hair cells fire itself, encodes the frequencies in the acoustic signal. And this one is also known as the frequency theory, hopefully for obvious reasons, but just the idea that you're sending the same frequency number of signals into your brain as you're getting from the outside world. But the problem with this one is that the cell firing rate itself is limited to 1,000 hertz. Your hair cells can fire off those electrical signals 1,000 times a second, which is amazing. That's not enough to get us up to 20,000 times a second, which is the highest frequency that we can hear or are sensitive to. So again, something more has to be going on. There's another theory called the Volley theory, which kind of attempts to work with this frequency rate proposal. So the idea here is that frequency rates higher than 1,000 hertz are volleyed back and forth between individual hair cells. They call this volleying, or use the verb volley, which I think of as like, one of these rallies back and forth in tennis or something like that. I guess volley is when you're up at the net and hit it without a bounce. But either way, I think I would use the word relay for this. So the idea here is, let's say you have a sine wave of 800 hertz coming into your ears. And then there's different cells which may respond to that sound, because like I said, the cells they're most sensitive to particular frequencies, but they respond to a range. So let's say these cells A, C, and E will respond to each peak of this sine wave. And they're doing okay because they can keep the firing rate going within 800 hertz or so. But then we get a 3000 hertz sine wave, which is happening much more quickly. This one also looks a little less intense. In order to deal with that, the cells kind of have to relay the message between them. So first A fires, then B fires, then C fires, then D fires, then E fires. Then we go back through the cycle again. And they're not responding as much as they were before because there are 5 different cells to work with here. So each one only has to respond 600 times a second. And they can handle that, evidently. But they have to be somehow coordinated to make this sort of sequence work in response to the particular peaks of the sine wave. So this is the Volley theory. If you want to call it the relay theory, you can, but I may be the only person in the world who does say that. But the metaphor there would be that one cell kind of hands it off to the next and then to the next and so on and so forth. A bucket brigade theory. Yeah, let's not call it that. Anyways, apparently there's a lot of evidence for this proposal. A lot of this gets into the nitty-gritty of speech and hearing sciences, which unfortunately I'm not really a specialist in, but I'm happy to tell you about the overview of them. And last but not least, there's also what's called the traveling wave theory. And this one kind of lines up fairly well with what we already know about resonance and filtering of sound. So the idea here is that the waves of different frequencies travel to a different extent along the cochlea. So this is sort of like wavelength, and I mentioned this idea before. So the higher frequency waves are going to have a shorter wavelength. Or you can think of like shorter twos will resonate at a higher frequency, that analogy. And the lower frequency waves will have a longer wavelength. And this is kind of what it looks like in the cochlea. So remember, we have the stapes, the last bone of the ossicles here, pushing back and forth like this through the oval window. And then the round window is going to kind of bulge out back and forth in response to those vibrations. But this is the endolymph being pushed back and forth here in the cochlea. And this will vibrate at different frequencies, right? So sometimes slower and sometimes faster, if I can do that. And the idea is that there's kind of going to be a sweet spot in terms of how the endolymph responds to that, such that it will get sort of maximum vibrations or deflections of the basilar membrane at some certain point along its length. And so for a higher frequency wave, it's going to be at a shorter point along the basilar membrane, and for a lower frequency wave, it will be a longer wavelength, so it'll be down here somewhere. This one's kind of in the middle. But you can see it's getting sort of maximum deflection here at this particular point. So this is the traveling wave theory, because these waves are being pushed through the liquid in the cochlea. And the upshot of this is that the lower frequency waves, as I mentioned before, will kind of travel the whole length of the cochlea. But higher frequencies will be cut off after a shorter distance. So all of the cells will respond to the lower frequencies to some extent, but fewer cells will respond to high frequency waves again. So like all the high frequency waves will be kind of clustered around here. The lower frequency waves will travel all the way down here. So the entire basilar membrane will respond in some fashion to the lower frequency waves, but only this part of the basilar membrane will respond to the higher frequency waves. And I don't know. Yeah, never mind. Had a theory there, but obviously it doesn't work, so I'll just move on. Here is a representation of sort of the response you would get at different distances along the basilar membrane from the stirrup or stapes to sounds of different frequencies. So like I said, the longer or lower frequency waves will kind of get responses that are longer in distance here, sort of towards the tail end of the whole basilar membrane. So you get this amount of response at 3 centimeters, you get this amount of response at about 3.5 centimeters, so on and so forth. These look like kind of like bell curves, which are skewed to some extent, sort of with the peak more towards the right than this long tail, which again stretches out more towards the base of the cochlea. And they're kind of in the same shape throughout. They're just kind of, the peak is pushed further and further down. We get lower and lower frequencies in this particular case. But you can think about this as individual hair cells functioning like low pass filters. So not all of them are going to respond to the high frequency waves. So the hair cells at 2 centimeters are not going to respond at all, basically, to the 2000 hertz wave. So it loses that high frequency information, but it will respond to the lower and lower frequencies, including 600, 250 hertz. So it cuts off frequency response at a certain point. Here's what it looks like if you kind of get the number of action potential spikes per second for an individual hair cell responding to sine waves coming into the cochlea at different frequencies. So this one happens to be tuned to around 1600 hertz or so. And this kind of looks a little bit like maybe a resonator or a filter in talking about acoustic physics terms. So there's a certain range or bandwidth of frequencies that a hair cell will respond to better than others. So this one gives us a nice little range from like 1000 to 2000 hertz for a low intensity sound. And these are the number of spikes it produces per second for these various frequencies. When you hear a higher intensity sound for the same hair cell, it's going to just emit more spikes, even though it's sort of still tuned to the same center frequency or the same sort of characteristic resonant frequency. So like I said, each hair cell has one frequency it likes best, but then there's a range that it will also respond to, and it's going to respond better to the lower frequency sounds than to the higher frequency sounds. At the high end, it will cut off at some point because it's a low pass filter, as it were. Okay, so in reality, there's probably more than one truth, which makes our lives complicated, but life is complicated, and trying to simplify things through science, just simplification cannot be our only criterion. We also have to have truth as our other sort of guidepost for creating scientific theories. So the truth here is that the traveling wave theory probably is more important for frequencies above 1000 hertz. And the Volley theory is probably more important for frequencies below 1000 hertz, which is a little bit ironic because this is sort of the cutoff for the firing rate of cells. So you'd think that they could handle, that would be come into play more for frequencies above this, but they still make use of this sort of relay idea for frequencies below their firing rate limit. And then traveling wave theory will work better for frequencies above 1000 hertz because, like I said, it's kind of those are like the high frequencies you can think of in those terms, and that's kind of what gets cut off by those sort of low pass filters that the hair cells form in our cochlea. One interesting fact about hearing is that the higher you go in frequency, the less precise your perception is of particular frequencies than when you're listening to low frequencies. So if the Volley theory is what's giving us sort of frequency perception below 1000 hertz, it is possibly what's feeding into the fact that our frequency perception is better at this range than it is above 1000 hertz. We can also add into this the fact that we kind of simply have more or a longer part of our cochlea devoted to these lower frequencies to begin with. So this whole like turn and a half of the cochlea is devoted to the frequency range below 1000, and then another turn and a half or two is devoted to the rest of the frequencies higher in the scale. But you got to jam in 19,000 hertz of frequency into this other half and just 1,000 into this lower half. So those lower frequencies matter to us, or at least our hearing systems are designed to respond better to them. And it's possibly because of these various mechanical reasons. But we have to kind of keep this in mind when we're considering how people actually perceive sounds and speech in particular. So here's an interesting phenomenon which was used to develop what's called an auditory scale of frequency. Hopefully this will transmit okay on this recording. I always worry about playing these demos for this particular lecture in class because it's easy to play them too loud and damage people's hearing, which is the exact opposite of what I want to do with this lecture. But what we have in this particular case is a tone of a particular frequency. I'm not going to say what it is, but I'll play it for you. Hopefully you can hear that. I think we can get away with turning this up a little bit louder. So let's try to match this tone to one of these three. And these three are going to each be at different frequencies, but one of them will be at exactly twice the frequency of this guy. So I'm going to play these three. I'll play them twice, and maybe you can tell me, or maybe you can think in your head, which one of these tones is exactly twice the frequency of this original. Okay, we'll do that one more time in a slightly different way. So I don't know if you were able to match that up exactly, but hopefully you can tell that these are all different frequencies. The one that is the match is the middle one. So this is 100 hertz, this is 195, this is 200, and this is 205. So these two are the ones that double it. Okay, so maybe you got that right. At the very least, you probably made a reasonable guess about them. Let's try this higher up, and this is where I get a little bit worried. So this is going to be a higher frequency tone. A little annoying. Let's try it that way. You can turn your volume down maybe if that's too loud, but here we go. Okay, I think in 13 years of doing this, I've had one student raise their hand and say, it's that one, where they felt like they really knew what the answer was, and they were correct in that particular case. But most people do not get this very easily. So this is 1,000 hertz. This is 2005. Sorry, this is 2005. This is 1,995, and this is 2,000. So these are the two that match up as doubles, and these others are a little bit off. And if you can hear that difference, great, because I cannot. And that's just how our hearing system works. These are, in terms of physical acoustics, these are each 5 hertz apart from each other, just like the tones on the previous slide. We can hear those differences relatively easily on the previous slide, but these, it's not easy at all, if maybe completely impossible. So there's an idea. There's a couple of different ideas about how to represent this, but basically the idea is that there's an acoustic scale of frequency, which we know is valid for what's going on in the air molecules in the world around us. But then there is sort of a different world inside of our heads in terms of how we're representing those pitches based on how our hearing system works. So one idea is that listeners interpret the pitch differences as absolute distances between the hair cells and the cochlea. And because we have sort of less space devoted to those differences for the higher frequencies, it's harder for us to get precise about that than it is for sort of the lower frequencies close to the apex of the cochlea. So one scale for representing this phenomenon is called the Mel scale, where perceived pitch is expressed in these units called mels, which I think is short for like melody. So this is using kind of a musical analogy, but twice the number of mels is supposed to be twice as high of a perceived pitch. And there's a very specific equation you can use to make this conversion. People don't use mels a whole lot in phonetics research, but I just want you to know about it anyways, because sometimes you encounter it. So it's this constant times the natural log of 1 plus the frequency over 700, where frequency is expressed in hertz. That's a lot. You can look that up if you really ever need to use it someday. This is what the scale looks like itself, comparing the acoustic hertz scale. So how many repetitions do we get per second on this axis compared to the Mel scale? So these units of perceived pitch over here. And the idea is that this is mostly linear. It's mostly a 1-to-1 relationship down here below 1,000 hertz. But above that, on the frequency scale, it starts to tail off into what looks more like a logarithmic scale. So we go from 0 to 0 to 1,000 to 1,000. By the time we get to 2,000 hertz, we're at like 1,500 something mels. By the time we get to 4,000 hertz, we're at 2,100 something. So there's less sort of differentiation between mels here for higher frequencies in the acoustic scale. And this reflects basically how our hearing system works. Based on that sort of, can you compare or decide when one particular pitch is twice the perceived pitch of another. I'm going to mention as well that we perceive loudness in a way which is dependent on frequency as well. So normally we think of loudness as sort of representative of the amplitude or the intensity of a sound, and we represent intensity is measured in decibels when we look at sounds. But how we actually perceive that intensity will depend on what frequency a sound is being played at, and this is the sort of really dangerous demo. So if any of those previous sounds have sounded too loud to you, please turn down the volume on your computer so you don't rupture your eardrums, as I mentioned before. So I'll do that here because I don't want to do the same to myself. But this diagram, it's generated, there are these psychoacoustic studies that were done like almost 100 years ago now by this guy named S.S. Stevens, who sort of tested the hearing abilities of, I think, undergraduates at like Harvard or something like that. Like over and over again, he had them doing these mindless tasks, which is, I guess, what you get a Harvard education for. But anyways, he got these sort of very finely detailed graphs of how the human listening system responds to different frequencies and loudnesses and so on and so forth. So just to kind of explain here, you can graph out sort of how playing different sounds of particular intensities on the y-axis here that have particular frequencies here on the x-axis. And this is a logarithmic scale for the x-axis. You might notice it goes from 20 to 40 to 60 to 100. Then all of a sudden it jumps up really quickly. So it's kind of compressed that way in the x-axis. And this is a linear scale here on the y-axis. But superimposed on top of that are equal loudness curves is what they're called. That's the name of the slide. So the loudness, this is what you perceive. That's what these equal loudness curves are. And so it's giving you sort of percepts of intensity here, which are not actual intensity, but perceived intensity. So something which is like 1,000 hertz and 40 decibels will sound the same loudness to a human being if we follow this curve up. If we go over here, if it's 60 hertz and 70 decibels, which in absolute terms is a lot higher intensity rating, but to us it sounds the same. So basically, things need to be physically or absolutely louder here to sound the same as in terms of loudness as something sort of this range of frequencies. And we kind of get this sweet spot here. The things that sound loudest to us are right around this 3,000 hertz range, which, as I mentioned at the beginning of this lecture, is kind of the it's not kind of, it's the frequency at which your eardrum is going to resonate best at. So your eardrum, or not your eardrum, your ear canal is going to resonate best at. So your ear canal will amplify those sounds for you to make them sound louder. So basically these are the famous mid-range frequencies. If you're a musician at all, you've probably heard about them. And then sort of on the low end of the frequency scale, on the high end of the frequency scale, things don't sound quite as loud as they do in kind of this sweet spot of frequencies. It's kind of funny looking at this curve because back in high school when I would listen to music, we had this nice stereo that sat in the corner of my dad's office, and then I would just like occupy my dad's office, he was too nice to kick me out when I wanted to listen to music and he had work to do. Thanks, Dad. I would set the equalizer on the stereo as like a 5-knob equalizer, and I kind of set it in the same sort of pattern that had more loudness on the far end, and then it kind of went down to the mid-range frequencies and then popped up at the tail end. So I knew nothing about this at the time, but I just kind of, again, your body replicates what we found out through science, right? Or science like figures out what your body's actually doing, I guess is the better way to put it. Anyways, I'm going to play you sine waves of the same absolute peak amplitude at different frequencies. And you should hear the sine waves at this frequency being considerably louder than the ones at the low end. And this is kind of where we get into trouble, because these ones that are in the sweet spot tend to sound a little too loud. So hopefully your volume isn't turned up too loud, and we'll walk through the demos here. Yeah, that one's a little too quiet, so I'm gonna crank it up. So I think you can at least hear that. All right, these are all the same peak amplitude. Yeah, and these guys sound considerably louder, right? Versus, okay, so that's, again, just an artifact of how your hearing system processes the combination of loudness and frequency. They work together, and in the next set of slides, we'll start talking about what happens when your hearing system starts to malfunction or not work properly, and you can't hear things sort of in the ideal sense, like the students who worked with S.S. Stevens a long time ago. Yeah, so I'll see you guys in a minute.